Hello. So this is a surprise video for section 1.9. So the reason I want to sort of add this fourth video of this section is I want to do just one quick example that I realized I didn't get to in the original three lectures. Specifically, I wanted to look at how do we interpret a linear transformation when it is defined in this way. And so your book will often use this way. I usually won't, but it's certainly possible that I might include a question like this. I think you do have a question like this on your homework. What this says is, okay, we've got a linear transformation on two variables, x1 and x2, and it sends this vector of length 2, x1, x2, to the following vector of length 3. And so in particular, notice we're defining vectors as sort of sideways objects with parentheses instead of vertical objects with brackets. They're the same things either way, and I'll show you sort of how we can just turn these and look at them in the usual way. And then what I want to do after that is determine whether or not this matrix is one-to-one and onto, in order to just give one example where we actually fully row reduce a matrix, and we are able to sort of examine that matrix and look at some of its properties. So we know now that every single linear transformation, even this one, has some corresponding matrix. So first thing we want to do is find that matrix. And so what we know is that this matrix is going to send the vector x1, x2 to some vector. Well, this is a vector of length 3, and the way we can translate this into a vertical square bracket vector is by just rotating it 90 degrees clockwise, and it defines this vector in R3. And so I think when we look at it like this, figuring this matrix out definitely becomes easier. Because remember, I should be able to take now this 3 by 2 matrix, and every row should match up with x1 and x2 to give me a new row of my vector. So notice, whatever this first row is, I should be able to match up this first row with x1, x2 to get the expression negative 3x1 plus 2x2. Well, that means this first row better be this. And so what you can actually do is just sort of let each column, again, define coefficients of a variable. And you can alternatively fill it in this way. And so notice now if I do this product, I get this vector. And so this is the matrix associated with this linear transformation. So let's determine whether or not this matrix is one-to-one and onto. So I'm going to do a couple of row swaps at the start of row reducing, because I know I want a leading one at the top of this column, right? And so anytime I see a 1 in column 1, I'll almost always just move that 1 straight to the top. So I'm going to do row 1 swap with row 2. And now I notice that I also want a 1 in this position in the second column, and I already see a 1 in the second column. So after doing this row swap, once this row has become row 2, I'm going to do row 2 swap with row 3. And I think it'll make a lot more sense what I've done when I just write out the next step. All I've done is I've taken the top row and moved it all the way down. Right, and so you can do this by just a couple row swaps. And so this puts ones in both of the spots I want ones. And so now I can just use those ones to clear out the rest of the matrix. And so this wasn't, once I got the ones in the correct spot, it wasn't a extremely tough process. First step, I just cleared out this -3. That got me this. I had a -10 here because -12 plus 2. And so I just used row 2 to clear that out. I get a third row of all zeros. And then I just move up row 2 plus row 1 to give me that. And so this matrix, sure enough, looks like it's in reduced row echelon form. So now we can determine if T is 1-to-1 and onto. So we'll do 1-to-1 first. So it's a little tricky, right? I am often one to want to associate a row of all zeros with a matrix being 1-to-1. But specifically note here that that is not the case. I was getting ahead of myself. I'm one to want to associate a row of all zeros with having a free variable. But here it is not the case, right? Because I've got two variables, x1 and x2. x1 corresponds to a pivot. x2 corresponds to a pivot, or leading ones if you prefer. And so remember, how do we determine if a matrix is 1-to-1, or in this case, if the linear transformation is 1-to-1? Well, we say, do we have any free variables? Specifically, is there a variable which does not correspond to a leading one? And the answer is no. So, T is 1-to-1. However, notice, I do have this third row of all zeros. And remember, how do we determine if a linear transformation is onto? Well, every row should also contain a pivot. And since the third row does not contain a pivot, T is not onto. And so an interesting trick you can use. So you could have actually determined that this linear transformation was not onto from the moment you looked at the matrix. So the reason being is that, notice this matrix, and well, the way we've defined this transformation defines a transformation from R2 to R3. And so anytime we're going to a space with smaller dimension, anytime we're starting in a space with smaller dimension and going to a space with a larger dimension, the transformation will never be onto. And so that was this. For example, if we were going from, say, R5 to R10, you could immediately tell me that transformation is not onto. On the flip side, however, anytime we're going from a space with larger dimension to smaller dimension, that transformation will never be 1-to-1. And so here, this could potentially have been 1-to-1, right? Going smaller to larger, it's not going to be onto, but it could potentially be 1-to-1. Going larger to smaller, it could be onto, but it's definitely not going to be 1-to-1. The only time it can be both is where the dimensions of the domain and the codomain are equal. So sort of quick ways you could have told that this transformation was not onto. And so anyways, that wraps up now officially section 1.9.